Welcome. I wanted to say a little bit more about the Cauchy Central Limit Theorem, which was already addressed last time, a little bit more about the proof. First of all, the classical Central Limit Theorem deals with random variables, stochastic processes, which have bounded variance and bounded mean. So these are usually denoted with L2. It's a Hilbert space of random variables. And one can define, just to make this in the Cauchy case clear, one can also define a Hilbert space in the case we just want that this averaged variance, so called this risk, that this exists. So we take the variance on an interval from -m to m, and we divide by m, and we want this limit to exist. So this is our space of random variables which we consider, and then we prove this is the attractor of a singled out distribution, the Cauchy distribution, with parameter 0, 1, meaning 1 over pi times 1 plus x squared. So that's here for c is equal to 1. This is the Cauchy distribution, the Hannibal Lecter of all distribution, because it has not very nice properties from the point of view of, standard probability theory. A stochastic process, you add up random variables and then you divide by n. Actually, that's the nice thing about Cauchy distribution. You don't divide by the square root of n, but you divide by n. Then you have a stable situation. In the language of Feller, you have a stable a case, and you have still Cauchy distributed random variables, and that converges then if you always kind of normalize it so that the mean is 0, this Cauchy mean is 0, and the variance, this normalized variance, is equal to 1, then you get to the standard Cauchy distribution. The Gaussian distribution looks very much like the Cauchy distribution, but the Cauchy distribution goes down much slower, and it's not integrable. So that's interesting. It's kind of interesting also that these two kind of names are associated to mathematicians who lived about the same time. Of course, you could generalize this for any, interpolated between here and here, but I'm not fond of just generalization for the sake of generalization. And also, what happens is if you make it for general index alpha, then in the language of Feller, this index is deciding what renormalization map you take, then things are not explicit in general. So what is nice about the Cauchy case, it's really very explicit, similar than in the Gaussian case. And the key is this, one of the things I kind of just pointed out already last time is the key is just to see what happens on the level of characteristic functions. So if you look at the characteristic functions and then you take a sum of two independent random values with that distribution, you just get the square. These characteristic functions multiply, and you want, then when you just normalize it with that factor 2 in the Cauchy case, you want to get the same distribution. So that's a very easy functional equation. I call it the Feller functional equation. If you look at the logarithm, it's this functional equation. So there are lots of fixed points here. Any function which is linear here, doesn't have to be the same limit, is actually a fixed point of this renormalization map. And similarly, if you take the usual case, then you have the square root of 2 here, and then you have the quadratic function is the fixed point. That's why you have the e to the minus x squared half as the fixed point, the Gaussian case. So, but here this is linear. The reason why it converges is if you start with any function which has kind of a right limit and a left limit, and they are not 0, then it converges just to the linearized function, which is linear here and linear here. Now there are two things in order to see that if you are in this Hilbert space, we have to just say something about the function phi. So we want to have here a derivative which is not 0, and also here a derivative which is not 0. Actually, you want the derivatives to be the same. And you can kind of see that just by looking at the Fourier theory, just as you make a Fourier expansion of x, that's how you get the expectation. You make the Fourier expansion of x, right? Just on that interval from minus m to m where you are looking at it, and you make the Fourier expansion here. And then you express it in a complex way, so that you can look at the characteristic functions. And then in order that is 0, you want to have that the derivative. So this is actually for small k, and for small k, if you make m large, and then you only the small bk will really matter, and this is essentially just what happens very close to 0. You essentially just want to have that the slope at the right and the slope at the left are the same. So that assures you some symmetry, the symmetry of the function. We want then something which is negative on both sides, and so then the phi is e to the minus a constant times x, or just nearby at least, and then but the fixed point will be that, and that's the Cauchy distribution. So what we want to have to make sure is that we have these derivatives finite. So we want to have the derivatives not infinite. We don't want to have something like that where it's infinite. We also don't want it to be 0. That would not work here. So in order to do that, we make the Fourier expansion of x squared. That's what we how we get then the second moment. And if you do that, see kind of just some magic going on. That's essentially just you know, the discrete derivative. It's essentially kind of just c constant times k pi over c, where if the slope is c. So you don't want this slope to be 0, otherwise it would be go to 0 when m goes to infinity. But you also don't want it to become too large. With this, you really kind of just see with the Leibniz formula for pi fourths, you see that this is actually just c. That provides you the link between this kind of, if you assume that this kind of normalized second moment is finite, this is equivalent to the fact that the derivatives exist from the left and exist from the right, and you want them to be equal so that the average is equal to 0. So that's the connection with the Fourier theory. So that's it for today, and I might actually write this down at some point. Okay.